we are here today we're in 6-1, which is exponential functions. And today we're going to start off talking about the key features of exponential functions. So an exponential function, you're going to write that in your box, ETIAL, is any function of the form y equals a times b to the x. And there are limits on the domain of a and b. A cannot be 0, because if you have 0, then you're multiplying that by the whole expression by 0, which is just going to give you 0. And b can't equal 1, because if b equals 1, then you're multiplying that constant a by 1 over and over again, which doesn't change it. That's just a constant function, not exponential. And finally, b has to be greater than 0 as well, because if b is less than 0, if you think about what happens to negative numbers when you raise them to different powers, like if we had -2 to the first is -2, but then -2 to the second is +4. So, we can't have b be negative. So b has to be a positive number that's not equal to 1, and a cannot be 0. And then the next thing we're going to do is just talk about, generally speaking, what these equations look like. So for a growth function, they have a shape that looks like this. So they're flat and then they get really steep really fast. And they're flat on one end because they're going to get really, really close to 0. And if you think about, having a constant number, so if we had 2 and we started raising it to negative power, so -1 is going to give us 1/2, but 2 to the -2 gives us 1/4, positive 1/4. 2 to the -3 is positive 1/8. Those fractions are getting smaller and smaller and smaller, but they're never going to be less than 0. And so you have that growth. For a growth function, your b term is going to be greater than 1. So any number greater than 1 is going to give you some kind of growth. A decay function looks very similar, except for it's flip-flopped. It's going to get very steep and then go flat. So it falls. It's constantly decreasing. So for a decay function, your b has to be less than 1. But remember, it also has to be greater than 0. So this means you're going to have all of those decimals and fractions that are less than 1, but greater than 0. And a decay function has that general shape to it. So for example 1, there's a lot of key features that we are going to take into account here. The first is whether we're looking at decay or growth. And that is all going to be told to us by the equation that we're given. So if we look at this, 2 to the x, this is a growth function because b is greater than 1. So in this case, b equals 2 and a equals 1. And then we need to look at what our domain is. Well, you can plug in any number for x, right? So x can be any real number because it can be positive or negative. So our domain is -infinity to +infinity, or all real numbers, however you want to write that. Your range, though, as we talked about, it's going to get really, really close to 0, but never actually cross 0. So your range is going to be 0 to infinity, or y greater than 0. You are going to have a asymptote at y equals 0. At y equals 0. because, again, that function is going to get really, really close to 0, but never actually cross it. And then our y-intercept is actually going to be given by a. So in this case, a is 1. So our y-intercept is 1 or 0, 1. And the reason we get that is because if we put in 0 for x, 2 to the 0 is just 1. So I can go ahead and put that point right there on my graph. And then again, we can put our horizontal asymptote on there at y equals 0. And this is growth. So we're going to go up really steep and then get really flat as we go to the side. So then we look at our end behavior. End behavior is the last thing that we address when we talk about the key features. And as y goes to infinity, not y. As x goes to infinity, y also goes to infinity. So if you look, we've got that upward motion as we go to infinity that way. Then if we look at negative infinity, as x approaches negative infinity, y is going to 0 because it's getting really, really flat. Okay, so that was that function. So let's draw all this off here. Now we're going to look at this one. And what you should notice here is that our b is 1/2. Now 1/2 is less than 1, but greater than 0. So we're looking at a decay function here. And our a, in this case, is 5. So our domain for this is still negative infinity to positive infinity. So with all of these exponential functions, your domain is positive infinity, negative infinity, or all real numbers. Your range, in this case, is 0 to infinity again, or y is greater than 0. Because once again, we're going to have that horizontal asymptote right there. Now, we'll talk about shifts in these horizontal asymptotes as we move on. But for now, they're there. We're not doing any shifts quite yet. So our asymptote is again at y equals 0. Our y-intercept, remember I said, is always 0 and then our a term. So in this case, we're going to have 0, 5 as our y-intercept. And I'm going to go ahead and put that on my graph right there. And then this is decay, remember, so it's going to start off really steep and go through that y-intercept and then get really flat. So it looks kind of like that. So if we're looking at our end behavior, which is our last thing we're going to write about here, as x goes to infinity, so as we move to the right, our y is also going to 0. So y is approaching 0. And then as our x values move to the left, our y is going to positive infinity. So as x goes to negative infinity, sorry, my handwriting is awful tonight, you guys. y is going to go to positive infinity. So you'll notice that the end behaviors for a growth versus a decay are exactly opposite of one another. And that's because your graphs are opposite. Okay, now we're going to move on to example 2. So we're going to graph some of these transformations. Now this is where your domain and your range and things like that are going to shift just a little bit. So let's start here with g of x. And we're going to talk about how this changes our parent function. I'm going to draw the parent function on here in black. It always has a y-intercept at 1 and goes up like that. Now, this negative out front, it's important to note that that negative is not in parentheses, so it does not apply to the exponent. So that negative actually signals to us a reflection across the x-axis. And then that's pretty much all you need to keep in mind. There's no shifts, there's no anything like that. So instead of your y-intercept being 1, your a in this case equals -1. So your y-intercept is down here at -1, and then it just goes down like that. So they're exactly reflected. And then your asymptote is still right there at 0. Okay. Now on your next one, I want you to think about this one a little bit differently. So again, our parent function, I'm going to put on here in black for h of x. Got our y-intercept there at 1. And there's our growth. Okay, we're still doing growth here, but we need to pay attention to that -4. And if you remember, anytime you throw a subtraction out there or an addition out way away from the x, it moves your function vertically. So in this case, we're going to shift this whole function down 4. That's what that's going to mean for us. That means our asymptote goes down 4, and our y-intercept goes down 4. So we're going to be right there at 3. And then the shape looks exactly the same. It's just shifted down. So in this one, our y-intercept is going to be -3, because we're going to take that a and subtract what's out there on the end. So our y-intercept is going to be 0, -3. And our asymptote is at y equals -4 instead of y equals 0. So that's what a number on the outside like that does for your graph. Okay, let's look at some real world application for this. So on to example 3, we're going to look at this model. So the population of a large city is about 4.6 million in the year 2010 and grows at a rate of 1.3 for the next 4 years. What exponential function models the population of the city over a 4-year period? So when we're thinking about a growth rate of 1.3%, first of all, 1.3% is the same as 0.013 as a decimal. So you've got to change your percent into a decimal. And then if we're growing, 1, remember, is remaining constant. So if we add that decimal in, that's how we get our growth rate. So 1.013 is going to be our B term. And then we're starting out, so our y-intercept, our starting point, is that 4.6 million. So our exponential function that's going to model that population is going to be P equals 4.6 times 1.013 to the t, time in years. And we want to think about how the time changes. So that t is the growth. Oh, hold on. Let me say this a different way. That is the number of years since 2010, because that's where it tells us that we started. And then 4.6 again is our initial population. Goodness sakes, I hope you guys can read all of this. I know you can't, but just work with it. And then your P is your population after that number of years. So now, with B, if the population continues to grow at the same rate, what will the population be in 2040? Well, how many years have elapsed since 2040? So 2040 minus 2010 means that we're looking at 30 years difference. So our T in that case equals 30. And then P equals 4.6 times 1.013 to the 30th power. And now we have something we can put in a calculator. So you're going to be using Desmos or whatever you can find. I guess I could pull up Desmos on here for you. Desmos. Sorry, I should have already had this pulled up. Okay, and I like the scientific, so we're going to do 4.6 times 1.013 to the, let's see if I got a function here. There we go. To the 30th power. So our new population then is going to be 6.78 million people. So our population, 6.78 million people. So there's your first little application problem. Now let's look at exponential growth and decay in terms of a percentage. And when you're looking at your decay factor and your growth factor, that's equal to B, which is also your ratio between two values. But I want you to pay attention to this. The way that you find R, which is the rate of increase or decrease. So that's where we get our percentage from, is that rate. So here, if you're looking at growth, B equals 1 plus R, or R equals B minus 1. So I can't quite see that purple there, sorry. B minus 1. And here, B equals 1 minus R, or with the decay, R equals 1 minus B. So kind of keep these in mind when you're thinking about how to find your percent change. So example 4 says, a car was purchased for $24,000. The function models the value of the car in thousands of dollars X years after it's purchased. So X is our number of years, and Y is the value of the car. So does it represent exponential growth or decay? In this case, we're looking at decay. And the reason being is that we know that 0.8 is less than 1. So our B is less than 1, so we're looking at decay. Our rate of decay, remember, is 1 minus B, or 1 minus 0.8, which gives us 0.2. Now, if we're going to translate that into a percentage, that's going to be 20% decay, which means that it's going to decrease by 20% each year. So we're going to next graph the function in a reasonable domain. So a reasonable domain means that our X has to be greater than 0, because you can't own a car for less than 0 years. And your y is also got to be greater than 0 because you can't own a car or it can't go into, a negative value. So our function is going to show up kind of in this little model here. Now your y-intercept up here is 24,000, remember? And our next model is we want to know when the car's value, so when y is going to equal 5,000. So again, I am going to go to Desmos, but this time I'm going to pull up my graphing calculator. So I'm going to go back and we're going to graph this. And our graph was 24,000 times 0.8 to the x power. I'm going to have to zoom way out, but there we have it, right? So now I need to know when my y is going to equal 5,000. Again, I'm going to have to zoom way out so I can even get 5,000 on my graph here. Let's see. Oh, I did 2,400. I need 24,000. There we go. And if I look at this, and I look, maybe I can just trace it. There we go. If you just trace your finger up and you can look right there at about 5,000, we're sitting at 7-ish years because our y value is 5,000. So we then know that after 7 years, our car is going to be right at $5,000. And yeah, that's a real life question there, guys. Because a car does depreciate that quickly. Let me show you once more how to change your settings. If we take our y from 0 to 10, deleting it for me there. Or our x from 0 to 10, and our y from 0 to 6,000, and we're going to move it by 100. You can see a little bit better now where that point is. So you need to get familiar playing around with Desmos. Okay, finally, on to our next example, example 5. Museum purchased a painting and a sculpture in the same year. Their change in values are modeled as shown. Find the average rate of change in each work of art over a 5-year period. Which work of art's value is increasing more quickly? Okay, you need to remember the average rate of change is the slope between two endpoints. So on our painting here, we've got 0, 40, and 5, 64.4. So if we're looking at our slope, we do 64.4 minus 40 over 5. We're going to get 24.4 over 5. And then I'm going to go back to Desmos, and I'm going to find what that value is. 24.4 divided by 5 is 4.88. So this one, the slope is 4.88. Now, for our sculpture, we got to change that up just a little bit. So this one gave it to me at 0 and at 5 years. So that's what I'm going to use for my x value over in this equation is 0 and 5 years. So 50, we know, of course, that 0 is going to give us 50 for our first point. So we're going to have 0, 50 for our first point. And then for our second point, we're going to have to put in this equation to Desmos. So I'm going to do 50 times 1.075 to the 5th power, because we're going to try to do it after 5 years. And we get 71.78. So we're going to have 5 comma 71.78. So now our slope function is 71.78 minus 50 over 5. 70. Woo. Now, look at this loveliness. We're going to take that, we're going to subtract 50, and then we're going to divide that by 5, and we get 4.36. So our slope for this one is 4.36. So again, remember, slope is average rate of change. So in this case, the painting slope is steeper. It's larger. So a steeper slope means a faster increase. Or a steeper slope in the negative direction could mean a faster decrease. So in this case, the painting is actually increasing more quickly. Now, why do we talk about average rate of change? Well, again, when you're thinking about quadratics or curves, like an exponential function, you can't really find the slope. You don't know how fast it's changing. So by taking that average rate of change, you can figure out what it's doing over a certain amount of time. Our last one is example 6. And example 6 is just an error analysis question, and it's one that I want you to kind of think about. And I'm actually going to ask you to answer this in a quiz before I give you the answer. So I need to know the error that Charles made here with saying that this is decay. Why is this not decay? Or is it? And the answer is that 3/2, while it looks like a fraction, is actually greater than 1. And if you think about the decimal, 3/2 is 1.5, which is, in fact, greater than 1. So this is why this is not decay. This is growth. So when you have fractions, you can't automatically think, oh, it's decay, because some fractions are greater than 1. And then I want you guys to note this summary page and make